Thank you so much. I'm Haddi. I'm a third-year PhD student here at Virginia Tech. It's a beautiful day. It's 11 a.m. over here. And good afternoon, guys. Uh, I'll be talking about my research where we are trying to use some program analysis on the JavaScript to just try to identify and localize the track in JavaScript code and to isolate it and precisely block those JavaScript code in itself. Without wasting any time, I'll just spend like a couple of minutes establishing the problem first so that we are on the same page, and then I'll talk about our approach. Fingerprinting basically just collect your browsing data to just build some profiles. Similarly, on mobile phones, you also use some of the permissions and add identifiers for targeted advertisement and behavioral tracking. VR is not just about the game, but it also tracks the user movements to optimize some experiences and to build some behavioral profiles. When we talk about smart TVs or smart appliances like thermostats and doorbells, each and everything collects some sort of lifestyle data. Finally, the voice assistants like Alexa, they are always kind of listening and processing your commands for both service improvement and targeted advertisements. So basically, in short, every smart device in your home serves as a data collection point, gathering some sort of information to create a comprehensive profile of your habits and preferences. Now I'll just specifically talk about the web browsers because it's just like 25 minutes and I cannot just possibly deep dive into all of those domains. So let's, for the sake of this presentation, stick to the web browsers. So they are basically the gateway to this digital world, and they are very sophisticated data collection tools. So when you visit a website, you see sometimes the cookies, which are small data files that do more than remembering your login information, as well as they just do some tracking, your online behavior preferences, and even sometimes your search histories. But these cookies are just the tip of the iceberg. They are also browser fingerprinting and are less viable but highly effective tracking methods. They just identifies you based on your unique browser setting like extension, screen resolutions, allowing highly personalized yet intrusive user experience. Now, what's concerning is that this data is not only serves to build your consumer profile, but can be exposed to the data breaches or third-party sales. So while we enjoy this convenience of saved passwords and personalized browsing experience, it's really crucial to be conscious of the digital footprints we are actually leaving behind. Now let's slightly narrow our focus from web browsers to very specific role of the JavaScript in its aspect. So JavaScript play a very instrumental role in this whole user tracking and web browser ecosystem. So often running in the background, JavaScripts collect the data as you navigate through websites. And these scripts enable the real-time analytics, capturing those mouse movements, clicks, time spent on a page, and even form input in some cases. So these identifiers are sometimes so accurate that they can just track you off, even if you are using some privacy tools like VPNs or incognito mode. So the majority of the task can be executed merely by just embedding a simple JavaScript file in your browser, which is then assemble each and every user profile and track the user data. Now it's high time that we should actually just look into it, why this JavaScript being a silent operator has so much impact. Now let's take a deep dive into some of the statistics to just show the urgency of this issue. I'm just borrowing some of the stats from the Web Almanac 2022 report. According to this report, the medium web page load ships over 500 plus kilobytes of JavaScript. I mean, like, this is insane amount. When we are comparing this data from last 2019, then there has been an increase from 18.4% in the JavaScript usage for desktop devices. And what's even more concerning is the continuous rise in this trend. From 2021 to 2022, we also see an increasing trend of 10% increase in specifically desktop devices. Now, this means that a trend that shows that JavaScript files are becoming larger, which means they are doing a lot of good stuff, hopefully, but as well as some tracking. So as the size and the complexity of JavaScript grows, so too does its ability to track us in increasingly more nuanced ways. Now let's look at another set of eye-opening statistics, and this is the number of JavaScript requests per web page. So again, this is borrowed from Web Alumni 20. And last year, the median number of JavaScript resources loaded was around 20 for desktop. And moving fast forward to 2022, the trend was 31 JavaScript requests for desktop. I mean, this is just, you're right. I mean, like, this is 31 JavaScript requests on one specific page on Medium. Yet again, I mean, year-to-year analysis just indicate there is an increase in this number. And you know what? This actually reminds me of a black hole. When you are kind of in, you are in, and it just keeps on pulling you in more and more. It's like we are stuck in a JavaScript black hole where the more we surf the web, the deeper we are pulled into this abyss of data collection and tracking. Now that we have looked the broader trends and the statistics, let's just go back to see how this whole JavaScript magic, or what should I say, like sorcery, this works. So imagine you are visiting a web page, and the moment you land on a web page, a JavaScript request for analytics script is sent out. Now, server sends the response for the requested script, and this is just not a normal script. It's one designed to collect the user data, such as browsing patterns, time spent on the page, and even clicks. Now, this data collected just does not only just stay with this website you visited, it gets saved and processed by some of the intermediaries like Google Analytics, PubMatic, ExoClick, and there's a long list that goes on. So the first question is what these intermediaries do, actually. So this is simply package your data and share it with the advertisers, enabling them to, target you with some alarmingly precise ads. Now, for example, you search for a hiking boots once, and suddenly you are flooded with outdoor gear advertisement for weeks. It's a very complex but very well-oiled machine that makes our digital lives both easier and a little creepier as well. Now, it's clear that JavaScript is more than just a benign code, and it's a tool with some serious privacy implications as well. And we are essentially caught in the web where our data is being continuously collected, analyzed, and then monetized. But the next question, obvious question, is what is the solution that we have in a status quo right now? So now let's turn towards some of the solutions that we have in the status quo, and there are some of the practical steps that we can actually take to reclaim our digital autonomy. So content blockers like AdBlock Plus, uBlock, AdGuard, or privacy-centric browsers like Brave, they offer the very strong first line of defense against this kind of intrusive tracking. But let's not kid ourselves. I mean, this isn't one and done solution kind of stuff. And that's why we are even here and discussing, because we are kind of engaged in an ongoing arm race with these trackers. So as we develop new tools to protect our privacy, trackers also evolve to become even more sophisticated in circumventing these defenses. And this is why it is critical to stay updated on the latest circumvention techniques adopted by these trackers. Now, standing still is actually not an option for us as well. So now let's slightly dig deeper into how these content blockers actually work. So the basic backbone of these tools are the filter list. So these lists actually contain the rules that block specific JavaScript URLs or other elements from loading on the websites you visit. And there are filter list engineers behind this who tirelessly update, curate lists, and adapting to the new tracking methods and identifying novel scripts that need to be blocked. And let's just give the credit where it is due that without this, our first line of defense would be far weaker. Now, it's important also to recognize another issue, and that is the difficult decision that they have to make sometimes. Now, I'll slow a little bit because now I'll just try to build up a problem. So one such dilemma is where they have to allow some of these URLs and they have to put them into the allow or exception list. Why? Because it's essential for the website's core functionality. As simple as this is, like blocking it could simply break the website. And they are forced to make this trade-off between optimal privacy and practical usability. Let's talk about one of the possible cases where we might have to add the URL to the allow list. And one of the such cases is when trackers start bundling or mixing the tracking code with the essential functionality code, shipping it all as one single JavaScript file. Now, the question is why this is an issue. So This strategy actually places filter-list engineers in a catch-22 situation. Block the file, break the website, or let it through and compromise user privacy. Either way, it's a lose-lose situation for them. And this is just another recent evolution in the cat and mouse game of digital tracking, underscoring the need of more robust and adaptable solutions. To further underscore the escalating complexity of this issue, let's take some longitudinal statistics. Some of the research folks have shown that between 2022 to 2023, they have seen the increase in the trend of mixed JavaScript. They use the term mixed JavaScript for where the JavaScript is being combining both tracking and a functionality code has increased by 40%. Again, this rising percentage is just a wake-up call highlighting this urgency of this evolving problem in this domain. Another interesting part is let's talk about one of the key reasons behind this mixing, and that is JavaScript bundling. So JavaScript bundling is just a development practice in which multiple script files are combined into a single file for faster load times. And one of the very popular tools for this is the Webpack. Now the question is why this is again an issue. Well, bundling can be intentional or unintentional, but eventually it will mix the tracking code with the essential functionality code, contributing to the challenges we have been discussing so far. So according to the Web Almanac, 17% of the 1,000 most popular websites are already using the Webpack as their bundling tool. Given the current trajectory, we can anticipate that content blockers will face increasingly overwhelming challenges in the next 5 years. And to be honest, the Webpack download stats, as shown on the slides as well, are climbing at an impressive rate as well, making it a key player in the bundling scene. Now, this puts filter list engineers in a very progressively tighter spot where the line between what to block and what to allow will become increasingly blurred. They have to make a very difficult situations where they have to provide like effective privacy protection without breaking the essential website functionality. So if we project this out, then content blockers may find themselves in a situation where their efficacy is going to be severely compromised. And this is just more than a short-term challenge. It's potential long-term crisis for the user privacy. Now, as we point to the future, it's worth noting that some of the content blockers are already innovating to meet these challenges. They are just deploying some of the labor-intensive but effective techniques known as scriptlets. They are the tiny pieces of code that can actually block the specific chunk within the bundle JavaScript file. I'll talk more in detail in the next slide. But some of the pioneers in this space, including uBlock, AdGuard, and Brave, and there are some of the tools that are still not using or considering this route are AdBlock Plus and PyHole. So the first question that how these scriptlets basically work. So they have a rule matching mechanism which checks it against the filter list. If that matches the element or script on that page, it injects the JavaScript code into the web page before the target script executes. Now, the result is the scriptlet code runs and modifies the behavior of the web page original scripts, effectively neutralizing the unwanted elements or behavior like ads or trackers from running. Now, it has two limitations of these scriptlets. First, while scriptlets are very generic, their quantity is still constrained. Given this, privacy engineers must preemptively account for diverse web page layouts, multiple JavaScript techniques, and unforeseen challenges on it. And expertise in this domain is very essential, compelling them to manually design and optimize these scriptlets, ensuring broad effectiveness without unintended repercussions. And the second is prior to deployment, engineers meticulously inspect the JavaScript code to confirm the compatibility and efficacy of their generic scriptlet. Now that we have dissected this issue of mixed or bundled scriptlets, let's envision an ideal solution first, and one that's just not effective, but also scalable and automated. So imagine a tool that can intelligently analyze a script and identify tracking code that can be easily blocked or replaced by a stub code while keeping the other parts of the code intact or semantics intact. This would allow automated generation of scriptlets, obviously on a grand scale, and drastically reducing the time and effort required to create them. Such automation would free up the privacy engineers to mainly just specifically focus on reviewing these generated scriptlets before deployment so that they can just ensure the effectiveness. And if we could achieve this level of sophistication, then I think we can just take a giant leap forward in this fight against this invasive tracking. Okay, so the first question is, how are we going to label those functions or whatever the JavaScript code block that we want to as tracking or non-tracking? Because we don't have a ground truth right now in this space. So as we considering this ideal solution, and the first foremost challenge is like accurately label the code blocks within the JavaScript file as either tracking or non-tracking. And some researchers in this field have already made some strides using some call stack analysis to label these functions. Essentially, when a network request is initiated, its call stack is examined to determine the nature of the function triggering the request. So now we can simply just leverage the existing filter list to label the tracking network request. And when the request is initiated, we can cross-reference it against the filter list. And then we can scrutinize its call stack to categorize it as a tracking function or not. So for example, on this slide, on the left-hand side, you can see the tracking request call stack and the functions associated with it. And on the right-hand side, we have a function request call stack and the functions associated with it. Now that we have identified and labeled the tracking functions, the next logical step is to gather some more insights about these tracking functions. What are they actually doing? Are they actually accessing some local storage, document.cookie, interacting with specific web APIs, or making any DOM modifications, etc., etc. So again, for this, we simply employ a similar call stack analysis strategy. So whenever a specific activity like accessing local storage or DOM modification is triggered, we capture a call stack against it, as illustrated in this slides as well. We have captured the call stack both when document.cookie or when battery.manager.charging time is being called. Now we cross-reference this information with the call stacks we have already seen and identified against those tracking requests in the first slide. So for example, as you will notice, these two highlighted functions also appeared in the call stack of a previous tracking request. So this provides us some additional insights into the behavior of these tracking functions. So let's just map this whole call stack analysis so far we have done onto a graph-based model. So in this model, each function call becomes a node, and the relationship between them, be it invoking another function, accessing a web API, or modifying the DOM, becomes simply an edges. Now we have captured the call stack, analyzed some of the tracking behavior, and even mapped some of the tracking ecosystem on graph as well. Now, what is the next step? Well, in the spirit of the modern problem solving, let's just give it to machine learning classifier and let it figure it out. Since we have already collected a very rich data set comprising of function behaviors, interaction, and graph-based relationships for both tracking and a non-tracking functions. So feeding this into a classifier could provide us highly automated and efficient way to distinguish between tracking and a non-tracking functions. Now, let's talk about some of the numbers of the classifier. After training our classifier on the collected data, we just came to know that the classifier we have achieved like precision of 95%, meaning that 95% of the functions is identified as tracking were indeed tracking functions. And the recall rate is at 98, indicating that it caught like 98% of actual tracking functions in the data set. We also do some extra coverage analysis and throw some garbage functions in the call stack to show that models sustain the robust performance, and just do some adversarial attack on the model to see how much precision, recall, and F1 score drops. And the results are on the slide as well. And these results are, by the way, were very marginal. So the next step is, once we have a model which has like very good precision, accuracy in identifying the specific function calls in the JavaScript code as tracking or non-tracking, how we can just leverage it to just generate some scripted rules. For this, we have two things. One, the source code of the tracking script at the runtime, and second is the line number and the column number where the tracking function call actually resides. By using this information, we can locate the actual function call and replace it with a stub call that simply returns an undefined. As you can see on this slide as well, the original track function call has been substituted with block me function call, which is specifically engineered to return undefined. So not only do we have an automated way to identify these tracking functions, but we have slightly an automated way to neutralize them as well. We consider there are some limitations in this approach. We have highlighted them in the paper as well, but still it has still achieved like 84.4% of the functions without causing an error in this surrogate generation step. And the last question is, once we have those scriptlets ready, how we can replace them at the runtime. And there are multiple ways. I think there were like talks talking about manifest version 2, 3, and then there is like recently in browser, Google Chrome browser, they have like override built in for feature as well. So you can do it. But let me just give you a high level overview that whenever the web request is being initiated and it's flagged by our system as, that we have a scriptlet against this script, we can just simply replace that response of that original request with the scriptlet response that we have already created, which is a sanitized scriptlet version we have. All this happens like seamlessly without breaking the web page or causing any noticeable lag. We can talk more in detail about manifest version 2, how we can implement this in a Chrome extension using manifest version 2, version 3, and then at specific level. But due to like limitation in time, I can just skipping it over for this slide. Lastly, we also evaluate this whole end-to-end framework because the end goal eventually is to minimize the tracking functions, then minimize tracking going on the web pages, and third, we are not disrupting any functionality on the websites. So for this, we have like these 3 CDFs that we generated on 50% of the data set that we have done so far. And you can notice that there on the first, if you just look at the first CDF, you can notice there is a conspicuous decline indicating that our strategy is very effective in replacing the tracking function calls within the JavaScript. The second CDF focuses on tracking request. Here too, you can see a very downward trend post the deployment of the scriptlets. And the last CDF is the functional request count, and the overlapping trend implies that our strategy is doing its job by neutralizing tracking features, while at the same time not compromising on the core functional request of the whole system. So to summarize, our strategy significantly reduces the tracking functions and requests without sacrificing essential functional requests, thereby striking a balanced approach to the web privacy and functionality. Now, coming back to the problem that we have discussed about the scriptlets, lastly, let's revisit our problem and see how our approach basically helps in scriptlet generation in automated and more scalable manner. So we visit a website, check if script rule that matches script on that page. We simply replaces the original JavaScript code with our specific JavaScript scriptlet that we have generated for that response. Again, the eventual goal is that scriptlet code runs and modifies the behavior of the web page original script, effectively, neutralizing the unwanted elements or behaviors like ads or trackers on the website. And this solution is slightly more scalable and automated because it reduces the manual effort of the privacy engineers by being site specific and does not require any manual effort to create or evaluate scripts before replacement. That's it. Thank you so much, everyone. If you guys have any questions, you can feel free to reach out to me on my email or on Slack. Happy to take any questions in person audience.
Thank you.